Swayam Prabha. Digital India. Educated India.
Welcome you to these lectures on fluid mechanics. So today I will cover the fluid kinematics, the subject what I like most. So for today we will discuss about the fluid kinematics, and very simple way I can tell that how we can describe the fluid flow patterns. Okay. So looking that, I will give you very interesting examples today, and you should visualize that how the fluid flows it, how complex fluid flows happens in the real fluid flow problems. So for today I will talk about that, but let's see these reference books. I am putting it to Professor Radhakrishnan's books, which is Fluid Mechanics and Introductions, which is very concise book. Okay. And this book is very interesting books. It has the lot of component is there, and very concise way it has been written it. So if you are interested to read it conceptual wise, please follow this Professor Radhakrishnan's books, the Fluid Mechanics and Introductions. No doubt we have been following these two books of Sinjal Simbalas and F.M. White book. Let's come back to the today lectures. I will start with the experiment setups, which is called Helisa experiment setups, to draw the streamlines, the Stix lines, the path lines, the flow past in different type of objects. Then I will talk about one example problems, which the CFD solvers using the vorticity contour shadings first at triangular cylinders. Then we will describe about Lagrangians and the Eulerian frames. And as I said it earlier, when you talk about the fluid flow problems, we talk about three fields: the velocity field, pressure field and the accelerations field. But today, beyond the velocity fields, we will talk about accelerations field, also material derivative. And we talk about, we will have some example problems, we can solve it. For very simple way we can solve the example problems, which is at more late that GATE or the engineering service questions papers. So similar way we can have a example problems where we can solve for the velocities and accelerations fields. Then we will go for very interesting talk about the motion and the deformations of fluid flow. When you talk about the fluid kinematics, if you try to understand it in a solid mechanics, we describe the motions without considering the force component. Or I can simplify it, tell you that we try to describe the flow patterns. There is a force component is there, but that force component we are not emphasized. So when you do that, we call fluid kinematics. That means you are describing the fluid flow problems, that means velocity field, pressure field, accelerations field, trace field and the tensors, but we are not talking about the force components and all, which if you know the velocity field, if you know the accelerations field, we can always compute other components, the force component. If you know the pressure field, you can find out the uplift force, the drag force on a object passing by different type of the flow phenomena. So the process what I am talking about, that the fluid kinematics and the dynamics both are combined, complementing each other. They are not separate. But for you to have a easy presentations, we tell that we consider the fluid flow problems where just we are talking about descriptions of these fields, the velocity field, pressure field, accelerations field and the density field. So, we are talking about how does they vary, how do they vary, that is what is our prime importance. As I demonstrate many of the topic looking at that, then we will be talking about the motion and deformations of the fluid element. And as you remember it, I introduce you virtual fluid balls. I think today we will use very extensively these virtual fluid balls to describe the Lagrangians and Euler descriptions, describing the velocity field and try to understand very easily the flow patterns of pressure field, velocity field and the accelerations field in a very complex problems using virtual fluid ball concept. That is my idea, and that is what today we will have very extensive explanations of the fluid kinematics using virtual fluid balls, okay, virtual fluid balls concepts. So, let us have a today lectures, and let us start with the experimental setups which we call Helisa apparatus, okay, where we can generate the constant flow, and there are the patterns of the color dye we can inject it. As we injected the color dye from these color dyes follows the path lines or the sticks lines. As we make the flow in steady, so the streamline and sticks line, when you look it, if I put the color dye, so this what will be show me the stick lines or the path lines, if I tracing on that, okay, path line or stick line, or since it is a steady flow, I can tell it that is a streamlines. So, many of the times we are very much familiarized with the streamlines, but when you look it, so what are these lines? Is that the streamlines, different colors, flow passing over this object. So, we can see that how the streamline patterns are happening it. As we change the flow Reynolds numbers, this pattern changes it. More we will have a discussions that how the flow passed an object, we have to describe it, but this is the experiment we have used it to plot the streamlines using a color dye and uniform plate flow. Okay. So, that is the reasons in a graph paper we trace these streamlines, straight the streamlines. As we control the flow, we will have a different velocity, different the discharge, you will have the change of the flow patterns. That what we do using Helisa apparatus setup which is there in IIT Guwahati. Now, if you look, it is very interesting experiment numerically is done by Professors Amresh Dalal and the PhD research scholar who developed the CFD solvers, and they have very unique lab which is called SwayamPrabha CFD lab. So, I acknowledge there these PPT to that. Okay, let us understand what is this PPTs. If you look at these colorful things, what it happens is that there is a triangular cylinders are there and there is a uniform flow, and they are just looking at vorticity, how the vorticity is going on. So, you can see that the vortex what is generated from the up and down, they behave differently, and at the different times the shading patterns are changing it. We will discuss about what is the vortex, but you can understand it, this type of vortex patterns happen if when you have a uniform flow passing through a triangular cylinders. Okay. The triangular cylinders, you will have this type of two-dimensional pattern of the flow. But if you just include a one small thread, if you look at that, the flow pattern changes it. Is that if you look at there is such a simple thread is there, and the flow patterns which is very interesting flow patterns what is happening it, that is what is changing it. the flow pattern of this and the flow patterns here. The streamline pattern, the streak line patterns, the path lines will be the differ, and there are the vortex formations happening in, and the series of the vortex, the formations and moving downwards is called vortex shading or vortex contour shadings, what is happening it. Okay. And that is what is they have a compare with the experimental data and the numerical presentations, what the varies of the central line, the average velocities and the x values, and they are getting very close to what is the experimental result. So, similar way we can conduct in experiments, okay, putting the triangular cylinders, and we can look at how the vortex shading patterns happens it. The same way we can do using these computational fluid dynamic solvers. So, if you look at today's, we have a very sophisticated softwares developed in IIT Guwahati, elsewhere also there are lot of solvers there. No doubt we can visualize the flow. That means we can understand which are the streamlines, which are the stick and which are the path line, how the velocity varies it, how the pressure varies it, how the density variations. So, those are things are today's it is a possible either through experiment or the CFD solver. It is a possible, and you see this in very interesting experiments, what the numerical experiment. These are what the numerical experiments which is done with a two conditions, with a just having a tail end part, here is nothing having tail end, and how the vortex shadings are happening it. So, if you can understand it, when you have a kite flying in the sky, there is a vortex shading just downstream of a kite also. So, you can try to understand it, or you can try to understand it if a bullet train, the train of more than 300 kilometer per hour is moving with that speed, with have a triangular shape, it can have a this type of vortex shadings. So, this process what we are representing is that you have what I am giving example is that let you have the not the triangular cylinders which is moving maybe very fast of 300 kilometer per hours, and it can have a vortex shading like this. It can have a vortex shading like this. So, try to understand these simple problems, what it happens for real engineering problems, that we try to understand it. Okay. Now, let us come back to that as given in the textbook, that we describe the fluid flow things, okay, descriptions of motion of the fluid flow without considering the force causing that motions. I just differ on this statement. There is a force component which causes the motions, but here we are not considering, we are not empathized. I think this considering sentence is not appropriate, but we can say we are not emphasized what is the force system. More we are oriented to know it, what is the descriptions of the motion of the fluid, as I demonstrated earlier, the flow fast in triangular cylinders. So, we are bothering about how the descriptions of the fluid flows. Okay. So, that is the reasons we will talk about now virtual fluid balls. Okay. That is the way the fluid motions are described in two fundamental ways. One is Lagrangian descriptions, is a long ago, okay, 1736, 1830s. The Italian mathematician describes Lagrange describe these motions, okay, that is what called the Lagrangians. Okay. Similar way you have the description of fluid motions with the field concept, and where that is the Lagrangian particle concept, what we call the virtual fluid ball concept, which is I can say that intermediate of that. That is what the way I try to represent you, that virtual fluid balls are intermediate between these, which not the particles or the concept or not the field concept. It is intermediate, so that student can visualize the fluid flow. And once you visualize the fluid flow, as you see that, you can solve many things, and or you can use that knowledge to interpret it, the very complex fluid flow problems solutions obtained from CFD solvers, as I demonstrated earlier. Very complex fluid flow problems, we can get a solution from the CFD solver. But the questions comes is, are they correct? So that's the reasons we need to have a basic fundamental knowledge on the fluid mechanics. And the concept of the virtual fluid balls used intermediate of these two descriptions, Lagrangian Euler descriptions. One is a field, okay, which we described earlier, the velocity field and pressure field and the density field, or we talk about the particles level, okay, fluid particles. That means a group of the molecules we are talking about. I think similar we are talking about virtual fluid balls is intermediate of particle levels and the field level. It is a conceptually the virtual ball, so that we can understand at the field level as well as we can understand at the particle level. That is my concept, and we are intermediate between these Lagrangians and the Eulerian concept. Now, we look at that what is the Lagrangians and the Eulerian concepts. Okay? If you look at a person is sitting here, so okay, he has a probe here and there is a industry, okay, it is a polluting the waters and that is the pollutions are released it here, is having the concentration C. Can have any pollutions, okay, maybe dissolved oxygens or whatever be, okay. There is a concentrations of pollutions are happening it and the pollutions loop is moving like this. If the persons who is putting a probe here, measuring that concentrations, okay, then we call Eulerian frames. That means you have a fixed locations. At that fixed locations, you are measuring how the concentrations are varied. That means this part. So, initially there will be some concentrations, but as the flow is coming it, concentrations will increases, as flow the concentration will go down. So, the C is a functions of T, the concentrations which is varied at the functions of T. So, we are not targeting about the fluid particles, we have the fixed locations. At the fixed locations, whatever the fluid particles are touching about that, those fluid particles, the concentrations we are measuring using this probe and we are plotting it. If we are doing that, then we call Eulerian frame. Okay? That is what is Eulerian frames. That means your position is fixed, you are getting the velocity field, the pressure field, the concentrations field at that point locations. If that persons will going to measure the concentrations at different points, then you can develop a concentrations variability map in a x, y and the t time, the space as well as the time. That is what will happen. The persons what is A, which is Eulerian frame reference, if he can use this concept, not the single probe, if he can put let be 100 probes, okay, and measure the concentrations and develop the variability of the C with respect to positions and the time, then we will have this function. Other one is that Lagrangian frame. What do you mean by that? Look at this particle P, okay, there are persons, okay, with a boot, he is just traveling along the rivers, measuring the concentrations. As it travels it, that means is a particles are moving it, okay. These fluid particles are moving it or virtual fluid balls are moving it. That is what we have concept, that the virtual fluid balls are moving it. As the virtual fluid balls is moving it, as soon as it reaches here, the concentrations increases, and as it goes through these, then concentrations decreases. So, you will have these functions. So, if you have not a single boatman, you may have 100 boats are there, okay, or you have the 100 virtual fluid balls. Then you can visualize that how the C varies with respect to positions and time. Since we are describing these concentrations field based on two ways the measurement. One is using a particles as particles moving it, or another is using the probe. We have a fixed locations, we are not bothering about which particles are coming, which fluid particles are hitting over that, but with that locations, with a time we are plotting it how the C varies with respect to time. So, this is a Eulerian frames descriptions of the concentrations. This is what Lagrangian frame of descriptions motions, where we track about the series of the fluid particles or the virtual ball, how their concentrations are changed, and based on that we have defined it that how the flow patterns are happening. So, either in a Lagrangian frame or Euler frameworks, there is no problems. Euler framework is a very easy because you are not looking at particles levels. But today world, as I introduce you to the virtual fluid balls, we can have the earlier they used to tell it, we cannot follow the Lagrangian frameworks, because to describe this flow field, the concentrations flow field, we may need 1000 numbers of the particles to describe it, which is too difficult to do it earlier. But now it is possible because you have a computational facilities, you can track it and you can visualize the fluid flow. So, that is the reasons I have introduced you about virtual fluid balls, which is just intermediate of this, and you just think it, you have the balls, thousands balls, I am ruling it, these thousands balls here. As the balls moves it, for each balls, how these concentrations are changes it, and that concentrations if I plot it, I will get the C variability in terms of space and the time. Or if I have 1000 probes, putting it in 1000 locations, measuring the concentrations, also I will get a C field. So, this is the field descriptions, this is the particle description. As in your textbook say that the Lagrangian approach is not necessary, I do believe that could be long back, but now having so big the best computational facility with us, today we can think it intermediate, the virtual fluid ball concept, where you can think it two ways how to understand in a Lagrangian frame as well as the Euler frames. There is no supersede of Eulerian frame in respect to Lagrangian frame. Let us discuss both the frames are equal levels, because today what the complex fluid flow problems we are solving it, the field approach also fails it many of the times. We should also look at the Lagrangian frameworks which are easy to understand it as compared to the field approach. So, let look at when you talk about this Lagrangian Euler descriptions, okay, the most interesting things we should talk about, what I told you that I have the pressure, okay, which varies with the positions and time. I have the velocity factors which is varying with the positions and time, and I have the densities which varies in positions and time. Either Eulerian frames or the things, but if you look at, there is a space coordinate, there is a time coordinate. Any variables, the velocity, the pressure, the accelerations, all the component we should look at in a space time diagrams. Okay. I think many of the fluid mechanics books they do not tell it, but I do encouraging you just think it. The time is another dimension as it x, y, z dimension. As we have the space dimensions x, y, z for Cartesian coordinate systems, similarly we have the time dimensions. Always you plot the x, y, z and the t. Then you try to understand the process. Okay, we do not have a 4 dimensions representations, but we can always think it that we can present the things in a space and the time diagrams. Please try to understand, I can describe this process of pressure field, velocity field, density field with in a space and time diagrams. Okay. That means there will be x and y coordinates, z coordinate and the time coordinate. That is a 4-dimensional component. Okay. So, you try to understand that way we can define the fluid. And if you know it, how does it vary, the velocity, the pressures, the density, accelerations, then it is easy to visualize that. So, always we should have a 3-dimensional perspective view of how do these the fields vary, and if you can understand that, then we can solve many of the problems. That is the reasons I am putting these graphs of 3-dimensional graphs to you. We just told it in the last slides that we measure the concentrations, which varies with positions and the time. Okay? Here is position only the x coordinates along the x directions. Okay? So, which can define is a functions of x and t. The plot will be like this. Just look it. Okay? This is a function of the x and t. The plot between x and the t and the c is varies like this. So, this is the space time diagrams. This is what? Space time diagrams and plotting the concentrations. Space time diagrams where I am plotting the concentration. If I put it a particular virtual fluid balls, as a boat is moving it, it has the velocity. As the virtual fluid balls are moving with a different time, I will have the velocity in x, y, z directions. I can write it, it is a functions of the time. Is it correct? In a Lagrangian description or the virtual fluid ball concept, if I were only loading a balls or the particles, I describe the particles velocity component of Vx, Vy, Vz as a functions of a time, because we are tracking the velocities of the particles. So, if I have a n number of particles or the virtual balls, so I can get this shape, and those concentrations can satisfy these equations, which will be the solutions what we are talking about. This is what our solutions, nothing else. So, that way we can define the Lagrangian specifications using the space and time diagrams with the velocity components, the pressure components, the functions of time. So, we are talking about the virtual fluid ball concepts in space and the time diagrams. How does they vary it? And if I know that variations of the virtual fluid balls, which will be functions of the time, may have the different functions with the time, and that functions, if I know it, I can know it how the c varies with respect to the space and the time. To demonstrate we have considered a 1-dimensional space in space coordinate systems and the time. Okay, that is easy to describe it, but you can have a 4-dimensional figures and 5th-dimensional figures, which we do not have to visualize you, but that is the reasons we have only the space coordinates in only one directions. Let me look at this Eulerian specification. Eulerian specifications, what do? We measure the velocity using the proofs and number of proofs in different points at the different locations. As you have done it that and measure the velocities and fit a functions with a x and t diagram, and that what is defined is the velocity field, which varies with respect to x and t. So, if you have the velocities having a 3 scalar component of u, v, w's and is varies with respect to x and the t, we can define their different functions. You can see it how complex things are happening it as you are getting from this function to this function and this function. So, if you just look at the shape of these functions, it is quite interesting. So, that way you can build a very complex functions to define the fluid flow. So, but in this Eulerian frames, since we define this velocity, the u velocity component, the scalar velocity in the x direction is a functions of positions and time, and the v is a positions and time, and w will be the positions and time. So, we define as a space functions and the time functions of u, v, w. And as I demonstrated you, just showing these three functions, how the shape changes, how the color changes. Okay? So, you can imagine it that if you have a two different variables, it changes your shape changes, your surface changes. So, any complex fluid flow problems we can define through these functions, because as with the simple descriptions of this what is showing it. Okay. That is the reasons I just encourage you as a students, please use the MATLAB code or mathematical codes which is available. Use these different functions and try to look at the functional behavior, visualize that. If you visualize that, really you will appreciate the fluid mechanics. Or many of the mechanics, if you talk about or the graphics, I think the tools today what is available to you as the MATLAB visualizers, mathematical visualizers, please use that to just visualize a complex functions, how does it looks when it varies in x and t. T again I will tell it is another variables. So, with a two space the variability is like this. If you talk about there will be variability in 3 dimensional, 4th dimensional, 5th dimensional, and you can imagine it what complex shape of the figures we can get it. So, I just encouraging you the students is please use the MATLAB visualizers, the mathematical visualizer, try different type of functions of 2 variables, 3 variables, plot it, visualize it. I think if you do that, you will appreciate the fluid mechanics. You will be engineers, which is that perfectly know what type of shape it is. Okay, that's the strength of an engineer. It's not like what is there in the textbook, but how do you visualize the equations or visualize the fluid flow problems, thermal problems. You talk about any problems, all we can use the functions to define the field. That is the reasons I encourage it. Please use MATLAB visualizers, the mathematical visualizers. Use different type of functions with a x and t, x and y, x, y, z, 3 variable, 4 variable, plot it, see it, how do they really vary it, and what complex the nature of the curve surface we get it, 2 dimensional, 3 dimensional surface. That what my point to tell you. Now, coming back to the Lagrangian frameworks, okay, which is nothing else, which is a partially fluid ball concept. So, that means at a time t I have a positions vectors where I know this the c which is varies with a t and this the a positions vectors. At the t plus delta t time there is a change of, let me I consider the velocity v is here. At this point this velocity changes v plus delta v. At the time equal to t plus delta t, the concentration changes it. It has a functions with a positions vector of r. The r is a positions vector is a depending upon accelerations and the time factors. So, if you look at that way, if I have the fluid particles, I can describe as a particles motions at time t and t plus delta t. The concentrations of that in that fluid particles, maybe dissolved oxygens, maybe BOD, whatever the component of the concentrations is that what is vary from t time to t delta t. So, this is what the position vectors, the particle movements at the t plus delta t we are describing to these concentrations varies from c, and how this also depends upon the positions vectors. At the a, at the initial position vector, at the t plus delta t we have a position vector, and you have the velocity vectors like this, which is having the scalar components. So, if you try to understand is that I have a n number of virtual fluid balls are there and I want to track it. So, that each fluid balls are having the velocity, and as at the time t it have a v velocity, at t plus delta t it will have a v plus delta v. There is a change of the positions, there is a change of the velocity, that means there is a accelerations, there is a force components.
So, if I am tracking up n number of virtual fluid balls, that means I am describing the velocity field, I am describing this the pressure field, I am describing the accelerations field, I am describing the density field. That's, and these things, how do they vary with the positions factors, that what we are illustrating it. So, that what the Lagrangian framework concept with a virtual fluid balls. Now, if you talk about that, as is told in many books, that when you describe the Lagrangian where the individual fluid particles will mark it, positions, their velocity and this. Same things I think I discussed in very beginning is that when you have a n balls should be considered and they should have a different velocity and their directions. Okay, V and V weights, the velocity factors can have a different directions, can have a different magnitudes and can have move any directions. Okay. But here, so that way you have a positions, their positions are changing it, the velocity is changing it, the pressure field is also changing it. That what we can find out to define this, the flow descriptions, that how the flow varies it, how the velocity varies, how pressure variations are there. Basically, when you do this in a Lagrangian framework, it is a very easy that mass conservations at the particle levels, momentum conservations, energy, we can apply it very easily as compared to the Eulerian framework, because we know it, we track of the fluid particles. But again I will tell that fluid flow is a continuum phenomenon, there is no doubt about that, that is what we discussed a lot. What my idea to tell it that nowadays, because we have a so sophisticated fluid mechanics tools are available, these virtual fluid balls we can use to visualize the flow, because lot of the solutions are available from the CFD solvers. There are high sophisticated instruments are nowadays available to measure the three-dimensional velocities, pressure field, but we need to now interpret that data. That data we can interpret it if we strengthen our flow visualization. How to strengthen that flow visualization? If I have a understanding how the virtual fluid balls moves it. If I understand that, I can have a confidence to analyze complex fluid flow problems, solutions what we get it from CFD solver, from advanced fluid mechanics labs having three-dimensional velocity, pressure measurements and all. So, what I am to debate it here, it is okay in a textbook, it is written it, the descriptions is not rarely used, but I can say in present era we should use the virtual fluid ball concept to understand more. What is virtual fluid balls? Again, if you talk about in terms of path line, streamline and stick lines, it is a path line. We have a particle concept, the Lagrangian concept. We already discussed about the path line. It is nothing else. It is a path line. Okay? It's a very simple thing. It is a path line. We are describing the path line of the Lagrangian concept. As I saw you the Helisa experiments, these are the path lines. We just individual fluid particles, we just dye it, give a color to that, and we track over that how it is going on. That's what is the path line. So, the Lagrangian concept is a path line, that is what we follow it. But in case of Eulerian concept, as I said that we have the probe, okay, and that probe has a positions x, y, z, where it is in terms of three-dimensional, and then you have the time we measure, like in case of the velocity. So, we define in terms of a scalar field of u, v, w, which varies with the positions and the time. These are the velocity scalar component in u directions, the velocity scalar component in v directions, means y direction and z directions, that what having a functions with the positions and the time. This is what the velocity field what we have described it. Either you can get it from CFD solvers or you can get it from very advanced fluid mechanics with the measurement facilities. Okay? But if you take a virtual fluid balls or the particles. That means you track upon that, the particles. That is what we described it. is the velocity, is a particle velocity at the time how it is varied. So, similar way, if I am looking at Newton's second laws, it say that force is equal to mass into accelerations. Force is vector component, accelerations is the vector component, okay, and both are the parallels. Okay. So, force and the particle at the particle levels, like in solid mechanics, the force we can put is mass into acceleration. Now, let us look at the particle levels. If I am to find out what is the accelerations of the fluid particles, is nothing else, is a time derivative of velocity of the particles. As you know it from class 10th, 11th and 12th, I am just doing this time derivative of the velocity, particle velocities with respect to the time, and that is what represents me accelerations. At the particles levels, you have this. Now, if you look at this, the velocities has a variability in a positions and the time. Because of that, when you derivative with respect to time, you will have a local component, okay. You will have with a x particle directions, y particle directions and z particle direction. This is nothing else if you are considering is a two variables, like I just discussed you the Taylor series. If you remember it, defining for the two variables, in this case I have a Taylor series of 4 variables, the x, y, z and the t. If you expand it and take it only these 4 terms, you will get this component, nothing else. We are near to the same Taylor series concept what we discussed in a single variables, independent variables, how the Taylor series expansion, the 2 independent variables, how the Taylor series expansion. If you do that, you will have the same concept what is there, and by the dt you will get it this compound. Now, mathematically we are not things, you just try to understand it that the same Taylor series we have applied it, but the V is having the independent, the variable 3 in a space and the time. That is the reasons you have the lengthy derivations. So, if you look at this way, the dx particle by dt, what is that? The velocity in the u directions. dy particles and dt, what is that? The velocity in the v directions. dz of the particles of dt, the particles, the change in the z direction with the times will be the, which is the definitions of the velocities. So, if I put it that, I will get it the accelerations fields as I explaining it that I will have a particles, the change of the position of the particles in the x direction with respect to time will give you the velocity component in that directions. So, this is for x component, so y component, z component. So, the finally this accelerations will have this form, accelerations will have this form. So, by transferring this, what do we do it actually when you talk about either particles of large number of particles or you talk about the proofs, both are the same in the both frame of reference. You will get it the same things, whether you particle track it and the proof it. You will have the acceleration speed like the same at the particles and the Euler frame of reference. You are getting it, this accelerations will have a 2 component, this component and this component. If you look at expanding forms, this is what vectorical representations, okay. It is called del operators, okay, between the v and delta. That is what the del, the dot product of 2 vectors, okay. That is what is represented this ones, if you remember it, the dot product of 2 vectors, okay. So, if you look at that, what is there? This the velocity is a changing with respect to time and it is given is a partial derivative. That means, with respect to time how much of variations, and when you are considering that, you do not consider the variability in the x and y z time. That what is called the local accelerations. That is what is called the local acceleration. But this component if you look it is called convective or adaptive acceleration. That because the particles are having different velocity gradient. Okay. Since they have the different velocity gradient, so let us look at this component of accelerations as particles or the Eulerian and Lagrangian frames, they will be the same. If you look at that, this is what is called the local accelerations. The velocity changes as with respect to the time only. So, that means at the probe locations, because of only the velocity changes at that locations will give us the local accelerations. Velocity also changes because of change of the velocity field. That is the velocity variance is x gradient, y gradient, z gradient and the UVW component. These component change of the velocities is called convective or adaptive accelerations component. So, there is two component, one is local accelerations component and other is convective acceleration. In vectoricals, we can very simple way represent it, the local accelerations and the convective accelerations component. Now, if you look at this same accelerations fields, if I am looking it as a delta operators or the gradient operator, if you know it, we can define it as ij functions like this, and the accelerations component, the scalar component of accelerations in x directions, y and z direction can have it like this. So, what we have done it, we just put it the accelerations ax, the u value, the ay is v value and az w value. So, all are the same. So, this is the convective accelerations terms and this is what we have local accelerations term. In a Cartesian coordinate systems where we have a x, y, z and the t, and these are showing these accelerations which will be ax I, ay j and az k. So, these are the acceleration scalar components in I, j and k direction respectively. So, we can define it the accelerations component. That means this equation shows that if I know the velocity components and the velocity partial derivative components, then we can know it what is the acceleration component. So, we can know accelerations variability in the space and the time. Space and the time, if I know this velocity variability, the partial derivative of velocity with respect to the space x, y, z, also the time variability of this velocity with respect to the time. If I know this component, I can compute this scalar component using this equation. You can easily remember these equations, which is just have a replace of u, v, w, it is nothing else representing the ax, ay, az component. But many of the times people talk about material derivative, it is nothing else. It is that the change, it is a special name of material derivative, means when you talk about a particles, along the particles you compute the derivative with respect to the time. It is a total derivative or the material derivative or the particle derivatives is nothing else. We already proved it that these derivatives we can define as these functions. That is what we have defined it. Okay. So, that means at the particles levels, how it varies with the time, it has a two component at the Eulerian frames. One is the local component, another is convective component. Those the gradient we have represented like this is a particle derivatives. That means it is the derivative of a particles are moving it. Material derivative, particle derivative, all are the same. The derivative as we are getting of the velocity field and pressure field, as I see that if I have a series of the boards, okay, I measure how does it changes it, that what is my total derivative component. Okay. But if I looking it in Eulerian frames, which will be this local derivative and convective terms, local derivative, local and convective term. This because of velocity gradients in a space domain, that is what we represent the accelerations. The similar way, if I talk the particles, it has some pressures. How these particles derivative changes to the time, I can define like this. if my particles having the density, as I earlier said that particle can have the density, my virtual fluid balls can have a different density. If I define that, I can define with a material derivative of that density dou rho by dt with the same way dt plus b with and the rho. So, if you look at that, either it is a density, the pressure or the velocity, all the things we can define in terms of particle derivative forms or the material derivative form. Some people tell different names, but all are the same. So, we are talking about in terms of Lagrangian framework to link it with the Euler frameworks, which is having a local and convective terms. So, that is a breaching between this derivative component between the Eulerian frameworks and the Lagrangian frameworks, the virtual fluid ball concepts, and that is what is linked as I said it. So, as this fluid having this velocity field, we can compute the accelerations field, we can compute this material derivative of the pressures, we can compute the material derivative of density with the same format, we can compute it and we can solve the problems in this way. Now, let us solve this very few two examples problems. One is that the velocity field is given to us to compute the material accelerations vectors, okay, as we discuss it at the positions has given it. After that, you obtain the component of accelerations is parallel normal to this p. Okay. So, let us solve the first part is that means I know the velocity field, I know this u, v, w components. Okay. I will do this partial derivative, substitute the bx, by, and the time derivative. There is no time components. Okay. So, there is these components becomes 0. Velocity does not have any time components, that becomes 0. So, we just substitute it and we get these accelerations, these ones. Then you substitute the at the velocity field this 141, this x position, y and the z, we just substitute it, get this velocity vectors. The similar way we get this acceleration as we substitute the value. Now, what is telling that you find out the component of accelerations which is parallel to the velocity. That means, we should do the dot product by magnitudes. Okay. You just try to understand the fluid vectors relationship, how to compute the component which is parallel to the velocity field. You will have this component and the acceleration perpendicular to these ones. I think you follow the any vector calculus book, you can find out how to, if I have a two vector velocity and acceleration vectors, how to find out the accelerations which is a parallel to the velocity and what is the acceleration component parallel to this velocity. Okay. There is a two vectors now. Okay. One is accelerations vector, another velocity vectors. Next question is asking is that what is the accelerations parallel to the velocity? That the components what we will get it here, and what is the acceleration component is perpendicular to this. That what just follow vector algebra books. Okay. Now, talk about another very simple interesting problems, that the velocity field is given to us. Okay, v, w, small b, u, all it's given to is this flow steady? You can look it. There is no time components. So, we can say this flow is steady. It is very straightforward. Is it a two-dimensional, three-dimensional? You just look it. There is a x component, y component, z component. So, it is a three-dimensional in terms of the positions. Now, at x, y, z, compute the velocity, which is very easy, local accelerations, convective accelerations. So, this is very easy problems as compared to previous ones. So, you know the velocity field, you know this u, v, w components, you know these accelerations, which is, this is part is local accelerations, this is part is convective accelerations. You, as we say this flow is steady, without doing any calculations, we can say that local acceleration is 0, because there is no time component. If this flow is steady, the local accelerations becomes 0. We need not to do any calculations. With some common sense, we can say that when you have the steady flow, local accelerations becomes 0, because your velocity field does not have a time component. It is independent of time. If it is that, there will be no local accelerations component. There will be convective accelerations component will be there. So, what we get it is a convective acceleration. That is what we solve it and get it this acceleration. Similar way, if you look at if velocity does not vary, these are all this gradient. If velocity does not vary in x and y z direction, my convective acceleration should be 0. So, you just imagine it, what is the velocity field is given to you. As I told earlier is that try to visualize the fluid flow by drawing these 3-dimensional figures in MATLAB or Mathematica. You have a lot of resources nowadays to have a 3-dimensional plots. Okay, even if in a Microsoft Excel we can have a 3-dimensional plots. So, make a 3-dimensional plot and try to understand how do they vary. As I told you that when you compute the accelerations field, if the problem is lacking, it is the local accelerations is there or not, first look at it whether the flow is steady or unsteady. If it is steady, independent to the time, there is no time component in u, v, w, we can say the steady flow, and we can say that local accelerations should be big zeros. Only it is a convective acceleration. Similar way, if my u, v, w all are constant, they do not vary with the time, all are constant, the convective accelerations becomes 0. So, you can visualize this thing. The problems of the fluid mechanics are too easy, but you try to understand the functions, how do they vary. If you understand that, you can use these simple mathematics to solve these things. Now, to compute the velocity field and acceleration field, we just substitute the velocity at the positions 1 and 1, what should be that and what should be the resultant velocities, as you know from vector calculations. Similar way, these local accelerations components also and convective accelerations component, we can compute it. So, we can have a references this. With this, let us conclude today's lectures, showing you very interesting photographs of 2D photographs which is available in internet. Today is 30th April 2019. Okay. You can see there was cyclonic formations happened in Bay of Bengal, wind directions and vortex motions. Is it not very interesting? We talk about a small helice saw experiment setup. It is a big experiment setup, big. Is it correct? Very big experiment setup with vortex formations. And these cyclones, we are predicting it, we are tracking it, what could be the cyclone. You see these figures, you try to understand how complex flow patterns happens during the cyclonic formations, how the vortex patterns, how the wind directions are changing it. So, we have a big experiment, natural experiment setups is the cyclonic formations, okay, not this small experimental setup, but the HELISA experiment setup with a color dye experiment. But today we are fortunate enough to see the process at different scale, smaller scales to much bigger scale. With this, let me finish these lectures with just showing you the summaries as I told it earlier. And today lecture I just spend a lot of time you to just understand what is the difference between Lagrangians and the Euler descriptions. And we talk about the velocity field and the acceleration field. The next class we talk about more about the motion and deformations of fluid particles, vortex, vorticities, all we will discuss using virtual fluid balls. Thank you a lot for this.